Hi, my name is Max George, and this is my presentation on wall-less liquid transportation for Organic Chemistry Lab 2. Throughout the history of men, uh, liquid transportation has become progressively more advanced. We've advanced from using ancient water skins to better containers like Yeti cups, which can keep things cold forever, or more advanced types of tubing that can move liquids more efficiently. One constant this entire time has been the assumption that you have to have a solid wall to actually transport a liquid. So not every liquid is the same. They each will have a different makeup on a microscopic level. Some liquids will be more delicate, more viscous, or more volatile than others. So when you're transporting a liquid, the method of transporting for one liquid may not be the same as for another. And so, commercially speaking, and honestly in everyday life, this has big implications. So, when transporting a liquid, you have to make sure that your container and the method of actually transporting it are correct so that you don't damage the liquid. Because certain liquids, their microscopic components can be damaged if you use the wrong method. So, some issues with transporting more delicate liquids that have fragile microscopic parts. Some are subject to destructive forces like shearing force. In others, is the potential for their microscopic parts to clog the conduit that they're being run through. And at this point, there are ways of reducing these destructive forces. Some of these ways are like hydrophobic coatings, surface tension pinning, and liquid infused porous surfaces. However, no option adequately reduces the damages that certain liquids undergo. So what is the solution? You have to stop using walls. So scientists have come up with a method called magnetostaltic pumping, and it is going to be, and I'll be referred to as the Q pump. So essentially, you're going to transport your desired liquid within another liquid. So the liquid that needs to be transported will be placed in a magnetic ferrofluid that the desired liquid can't be dissolved in. And a ferrofluid is a liquid that very small particles of magnetite have been suspended in. And so to transport them, the two liquids are going to be stabilized with a quadrupole magnetic field. And the definition of a quadrupole magnetic field is an electric or magnetic field equivalent to that produced by two electric or magnetic dipoles, whose dipole moments have the same magnitude but point in opposite directions, and which are separated from each other by a small distance. And then this magnetic field from the quadrupole magnetic field, it can be altered to suit whatever path that you want the liquid to flow. So say, for example, you want the liquid to take a turn in the circuit. You're able to manipulate the magnetic field to cause that. And right here I have a example of the basics of how this is set up. So you have here your water is in the antitube, so it's this thin line here, and then you have your ferrofluid, which is around it, and right here you have the magnets creating the quadrupole magnetic field. And so they're essentially making a current that's going around like that to keep them suspended. So this method is really great and important when you think of its applications for like the medical industry. So one liquid which has a lot of like small microscopic components is blood. It's obviously a very important fluid. We have to have it to live. And oftentimes like medical professionals have to transport it during like surgeries. So it's little microscopic parts are delicate and subject to damage. And so a concern with transporting it is that erythrocytes may go through hemolysis. And hemolysis is very dangerous because it releases hemoglobin, which becomes toxic at high levels in the body. So the Q-pump method was compared with a traditional method of peristaltic pumping. in order to see if Q pumping had offered any advantages. And so these were their results. So certain things were found the same. There was no significant difference with the hematocrit and cell counts, and there was no real difference with platelet function in the blood. But the big difference was that Q pumped blood had 11 times 10 to the raised to the 6th less hemolysis than blood which was peristaltically pumped, which is a huge difference. That's a very large number. So Q pumping was shown to potentially be able to stop hemolysis from happening, which would prevent hemoglobin buildup in the blood. So in the future, what they're looking at doing is focusing on using the Q pump on living organisms, and they're going to start doing that by using mice. And hopefully this will show that it's safe to use on biological organisms and can move on to human testing. And other things that they're looking to do with this are to transport biological fluids like plasma or antibodies, which are also made up of small microscopic parts which are delicate. And these are my references. Thank you.